Here we're going to be talking about moments in two dimensions. On the graph here I have a position vector r and a force vector F. Notice that this force vector tends to move r around the point O, the origin. And the number to watch is this m0, which is the moment of this force about the point 0. Notice that it's positive now, and this force is trying to move this vector r in the counterclockwise direction. If I move the force down the other way, so that it's trying to move this vector r in the clockwise direction, we have a negative moment. Now, we can move the r vector to the axis, and then the f vector up in the y direction. And we'll notice r is 6 and f is 6 in this case. So our moment is 36. If I move f down, let's make f minus 4. So again, r is 6 times minus 4 is minus 24. As long as these are at right angles, let's do it's fairly easy to calculate the moments. Here we have 4 times 4 is 16, and again it's trying to rotate it clockwise, so it's a negative 16. The other direction, we're at a positive 16. Now, we're usually not so lucky to have the vectors running along the axes or parallel to the axes, but we have an angle that we want to watch here. Let's see, let's put it this way. And look at the angle. And when we say the angle between the vectors, this is the angle we mean. If both vectors were at the origin, it would be the angle between the vectors. And here we've got 71 degrees for this angle. And if I move it over here, we've got minus 45 degrees. Again, when it tries to go clockwise is a negative angle, and counterclockwise is a positive angle. And we can use this angle then to calculate the moment. We see the equation for the moment here is the magnitude of this r vector times the magnitude of this f vector times sine of this angle. And this is easier to see, I guess, if we look at it in terms of a force projection. So if we project this force into a vector running in the same direction as r, and a vector perpendicular to r, this perpendicular vector is of course f times sine of this angle in magnitude, and the projected vector is f times cosine of this angle. And then we can just calculate the moment again as the magnitude of r times this f perpendicular. And again, if I move this around, we'll have to track the sign on f perpendicular that's trying to rotate clockwise, so it should be negative. We also look at this parallelogram. We can see the magnitude of the moment is equal to the area of the parallelogram formed by the r and the f vectors. This is similar to adding vectors with the parallelogram rule, but now we're looking at this area. So if we turn our projections back on so that we can see the projections, we'll notice that this area of this parallelogram, you can treat r as the base and f perp as the height of this parallelogram to get the area of the parallelogram. Then we can look at this yet another way. We can look at the components. So we will split both vectors into components. We have our f vector has a component in the x direction and a component in the y direction. And our r vector has a component in the x direction and the y direction. Now we can move these forces. We can actually move the components along their line of action. So we can move the components to the axes, components of the force to the axes so that they line up with the components of the position vector. Now when you do this, you'll notice in this case both vectors are in the positive direction, so they have positive components. But we'll notice that Rx times Fy gives us a moment, a positive moment, while Ry times Fx gives us a negative moment. And that's how we get this formula Rx times Fy minus Ry Fx. So it's the sum of these two moments gives us our total moment. And if we move F in the other direction, let's do it this way. Now here, the Fx component is negative, so we have Ry times a negative Fx, so this actually gets added. So it gives us our positive moment as everything is moving in the counterclockwise rotation. Again, we can see the counteracting moments from the different forces from the components. Now, one thing that is fairly interesting here is we can draw a line parallel to our r vector, and let's get it to snap there. Okay, here we see our moment is minus 24 in this case. We've calculated it out. Now if I move F to another point along this line, it's still minus 24. If I move F to any point that's on this line, we see the moment is the same. Minus 24. Well, notice the equations. If you look at the equations, and we have here, let's say R cross F plus R is what we want. And that is going to be the sum of R cross F plus R cross R. And we'll remember that R cross R, though, is going to be 0 because the angle between R and R is 0 and there. So here we have, again, R and F. And if I add, again, this vector R, I move it up 6 and 6. Eight and 6. Move it up from where it was. 1, 2, 3. Yep. Again, we have the same number. But you could have this R times a constant that would move it along this line. As it turns out, we can also move the R vector in the direction of F. So if I move the R vector in the direction of F and keep F the same, 1 minus 1 in this case, and I can move R this way, I have to move this F again. We're still at minus 24. So we can move R in the direction of F or F in the direction of R, the tip, without changing the moment. Now, the more convenient way to calculate, okay, we can look at the component projection. If we look at our projections, we can calculate the projection vector without using the angle, but we can calculate it. We have the magnitude of the projection vector. And that's from this formula. We use a dot vector dot product. Here, a bold letter is the vector form of the force, and the vector form of the position R, and a non-bold is just the magnitude of R. So we have F dot R over R to get the magnitude of the projection, and then this vector R over R to get the direction of the projection vector. And if we want to find the perpendicular vector, the thing to notice is if we take our F and subtract the F projection vector, it will be the F perpendicular vector. This applet is available online so that you can try all these things out yourself at the address in the comments.